Before I continue, does anybody have any questions about what we've done up until now? What I've talked about?
I would like to ask, what is a shim?
What is a what?
Shim.
Where are you looking at? Where's the slide you're looking at?
I will find it, just a second. You said that we need to use shims.
Oh, a shim. I thought everybody understood what a shim was. Oh, sorry. Let's go back to a shim. Okay. So a shim is basically actually, I think I have a picture of a shim. Let's see if I can quickly find that picture. That's a shim. See the steel plate underneath here?
Yes, okay, thank you.
This is a little bit thick. Usually you don't use a shim this thick. Usually use it, 2 millimeters, 4 millimeters, 6 millimeters, something like that. But a shim is a steel plate that you put underneath the direct fixed fastening to allow you to adjust elevation.
How do you spell shim?
Say again?
How do you spell shim?
How do I spell shim? S-H-I-M. Here, let's go back.
Okay.
There's a shim. Okay.
I have a question, please.
Yes.
About the concrete plinths
Yes.
on curves.
Yes.
Is it how do I say it, enough strong concrete to hold the rails? When you talk about the concrete grout?
No, you don't use a grout pad. Grout pad is not strong enough. You would need a concrete plinth.
Mhm.
So you need to go back here.
Yes. Oh, it's with iron. Okay.
Yes, it's all reinforced.
Yes. Reinforced.
Yeah.
Okay.
No, a grout pad you cannot use because grout pad is not reinforced. Grout pad is not. You're 100% right. Grout pad is not strong enough, but a concrete plinth, which is always reinforced, you can use. I think even the one without hair, you can see over here. This
So
is
it's a part of the tie or the sleeper? It's a part of the sleeper?
No, there's no sleeper here.
No sleeper. Okay.
There's no sleeper here. In this particular design, you have a concrete slab.
Yes.
And then you have your concrete plinths.
Okay. Thank you.
Now, actually, you led me into you perfectly lead into my next question. So there is another type of design. Let me see if I can find the picture and I can come back. There's another type of design where you use sleepers, or in this particular case, this is a 2-block sleeper without the steel bar. There are other cases where you use the 2-block sleeper with the steel bar, and in other cases where you use a monoblock sleeper, and then you pour your slab around the sleeper. So let me see if I get a picture of that. I actually had a picture back here. I'm going too far back. I may not be able to go all the way back. Here. So here's a case where you used a monoblock concrete sleeper and you poured your slab. So you sort of built your track with the sleeper, and then you poured your track in between. Then let's jump forward. Oh. Got carried away, went too far. And this is a case. So this, if you remember the two block sleepers usually have a steel bar in between. This is a case where you have the two block sleepers without a steel bar in between. And so this is actually acting as a as a plinth, in fact, but it's really part of a sleeper, and you're pouring a track around it. But whenever you're doing something like this, you actually want to put an elastomeric boot or a rubber boot around the base of the sleeper. So you can see over here, and you can see over here, you see this boot on the base of the sleeper. So for example, this is a system they used in the Channel Tunnel between Britain and France. They used a variation of this approach where they actually used it with the steel bar, so they actually were able to maintain the gauge. But you can see this is a top-down construction. They first pour the slab, then they lay the sleepers down, then they pour. They do a final pour in the bottom around here, holding the tolerances. And again, you can see the boot. You can see the elastomeric boot at the bottom of the sleeper. So you can either use, as I say, a two-block tie with an elastomeric boot. You can remove the cross member in between. You can use monoblock ties. The concrete blocks in the rubber boot are often called low vibration track. This is a term that's been used also because, again, it's designed to reduce vibration into the track. And in fact, you can see here, not only do you have a boot, but there's also another pad underneath the base of the block. So you have the concrete block. You have your direct fixation sitting on your concrete block. You have a pad underneath your concrete block, and then you have your boot underneath your pad. This is, again, is designed to reduce vibration. So the elasticity is provided here. And so in this particular design, you don't need as sophisticated a elastomer system or in your direct fixation fastening because you've added some additional resiliency underneath your concrete tie. So now you've got different options on where you build your resiliency in. Do you build the resiliency into the direct fixation fastening system? Do you build the resiliency between the underneath the block, between the block and the slab? All of these are configurations that have been used in the past. This is also designed to, again, attenuate dynamic loads. And again, you can have you can reduce the elasticity of your track, but your modulus is still relatively high compared to ballasted track. Even with all the pad configurations, you're still going to have a high modulus with respect to concrete or timber sleeper pad on ballast. Ballast is ultimately one of the best noise and vibration attenuation systems we have there. So with the
so why using concrete?
What?
So why using concrete? If
why
the ballast
using a
is good?
slab?
Yes.
Well, the most common reason is because
For low noise. I'm sorry, for low noise. For the purpose of low noise.
Because if you're dealing with a tunnel, then you have an issue of what diameter of a tunnel you have to bake.
Okay.
And if I'm introducing ballasted track, then I have an extra what, I have an extra half meter, I have an extra 500 millimeters, 600 millimeters of ballast that I have to accommodate in my tunnel boring. So you tend not to use ballasted track in subway construction or in tunnel construction. You tend to use slab track. The other reason you'll use it in very high-speed rail, the reason the Chinese use it in high-speed rail is it allows them to maintain tighter track geometry tolerances for very high speed. So if you're traveling at, if you're going at 350 kilometers per hour, your geometry tolerances are very tight. Both the Chinese and the Japanese have been using a lot of slab track to try to control that tolerances. But even most metro systems, when they build track at grade, they use ballasted track. You very seldom see slab track on metros at grade, because the maintenance costs, the construction costs, the noise and vibration performances are always better with ballasted track. But sometimes you can't have ballasted track, as I said, for tunnels.
Okay.
And so that brings me to sort of the next method of noise and vibration control for slab track, probably the most expensive and the most effective of all the techniques, and that's called floating slab track. Floating slab track is when I was involved a number of years ago with Tel Aviv Metro, and Rena, you have to tell me if it's still being the same way. But when I was designed, we used a lot of floating slab design in the tunnel because there was a lot of concern about noise and vibration. And in fact, there was so many noise and vibration areas that there was at least one proposal to use floating slab for the entire metro system, so you wouldn't have to keep changing designs through the track.
Rubber mats against the noise there.
Are you still using floating slabs in the tunnels?
We use rubber mat.
Rubber mat underneath the slab.
Yes.
That's a floating slab.
Yeah, exactly.
That's a floating slab design. Okay, so floating slab, let me go to a picture here. So in floating slab, I have my bottom concrete. I have a second concrete layer here where my fasteners and my rail and everything rests on. And then I have rubber or elastomeric pads between the two concrete layers. And you can see this is vertical and this is lateral. And a modification of this is if I just use a complete rubber pad underneath it. There are various arguments about which there are advantages and disadvantages to both.
Can I ask a question that everybody asks me and I don't have an answer? The life of the rubber mat is about 10 years, and the life of the mat is about 50 years. What's happening in between?
Okay, I don't know about the rubber mats. I don't have a lot of experience with the rubber mats. I will tell you, these rubber hockey pucks, they tend to be between 20 and 30 years. The major case that we ran into the United States was in Washington Metro. Washington Metro had floating slack sections with what we call the rubber hockey pucks. So they were.
It not depends on the MGT?
Yes, it depends on the MGT, but most metros have similar MGTs. Most metros are running between 20 and 30 million gross tons. It's fairly typical for a metro. You'll never see a metro with 50 MGT or more, and you usually don't go to this kind of expense to a metro that's running 2, 3, 4 MGT. you need enough traffic to justify it. So you're right. It is dependent on the MGT, but most metros run about 20 to 30 MGT. That's fairly common for metros. New York City, London, Paris, Moscow, they're at the higher end. They may be 30 to 40 MGT. But a metro, for example, like Tel Aviv, will probably be running 20 or 30 MGT. That's probably pretty realistic in terms of what kind of traffic density they're going to be running. So this type of elastomeric element we've seen last 20 to 30 years. Or if you're running at 20 to 30 million gross tons, you're looking at 400 to 600 million gross tons of total life. Okay. And what happens is then they have to be replaced. Now, the classic problem, I guess the classic case was Washington Metro. In Washington Metro, they did not have any provisions for replacing the rubber mats. And when the rubber, they call it the hockey pucks, they were circular diameter. You can see they're rubber bearings, about 300 millimeters and 300. I think the Metro ones were about 300 millimeters in diameter. And so there were no holes through the concrete to the top slab. So they literally had to break through the concrete to replace the bearings, which were a problem. Most modern designs have a hole. You can see here, there's a 400 millimeter hole right down the center of the track that's designed to allow you to go in and extract the bearing and replace the bearing. You obviously have to have, it's a fairly complex process because you have to make sure, you have to pull up the slab and then remove the bearing and then replace it. But that's the life we tend to see for the elastomeric pads. The people who have done rubber mats, they've been claiming long lives, but my suspicion is they're gonna. I think my concern is that, Rena, I think your life is going to be less than 20 years. I think your life may be closer to the 10-year life. So you're going to really have to watch that carefully. My experience with rubber mats have been basically under ballasted track, under sleepers and ballasted track, not so much in floating slab. So as I said, the floating track design consists of two slabs, the base slab, which is usually U-shaped over here, and then the top and the second slab, which includes the track structure. And then you use these elastomeric elements or donuts or hockey pucks to provide the vibration isolation. Also have to be really careful to make sure you maintain drainage. So here's an example of a floating track, floating slab in a tunnel design. Again, the bottom track has that U-shaped groove in here. This is the same picture we saw last time, just it shows the full tunnel configuration. This is a top view. So you can see in this particular case, these top pieces were, can be precast. I think in this particular design, they were designed to be precast. You can see the bearings. They're about 300 millimeters in diameter. There's a big access hole in the center that allows you to get to it. The access hole is a 400 millimeter diameter hole, so you can take it out. And in this particular configuration, you can also see the lateral pads. You see lateral pads, longitudinal pads between the slabs, and then the vertical pads. So in this particular case, you have elastomeric elements in all three dimensions, vertical, lateral, and longitudinal. Again, just to give you an example of one design configuration. So again, the mass of the slab has to be calculated to give you the dynamic noise attenuation that you want. So in this particular one, the mass is about 2,000 kilograms for each of these top slabs, which is about 2.3 meter by 1.15 meter by 30 meter. Sorry, other way around. This is the 2.3 meter this way. This is 2.3 meters. This is 1.15 meter. And then there's about 300 millimeters in depth. The stiffness of the rubber pads in this of the rubber pads in this particular case were about 5.56 kilonewtons per millimeter. For the side pads, the vertical pads were about just under 4 kilonewtons per millimeter. They were natural rubber. Well, you can see all the parameters. I'm not going to go through them. Now, one of the problems you run into is if you have a floating slab going into a conventional slab, going to a floating slab, you sometimes need to have transition zones. So you have a dynamically smooth transition. You don't want an abrupt change in stiffness because two things will happen. You will generate large dynamic loads and you'll generate corrugations. Corrugations, we see corrugations in the railed form in places where you have a significant transition zone, and you also get very large dynamic loads, which can cause degradation of the track. So very often you need a transition slab or an approach slab to provide you with a variation and to accommodate that variation in stiffness. Okay. Drainage. Not going to talk a lot about drainage other than it's really important. And you need under drains. You need drainage becomes a real issue with water that's trapped in, particularly in floating slabs. Same things we talked about with stray current protection applies to the floating slab. You basically need to make sure you properly ground any reinforcing metal. You got to make sure that you have a proper gateway for the grounding current to go to ground through the running rail. Okay. Direct fixation fastening systems. I'm not going to go through detailed design on this. It's really don't have the time. To properly talk about slab track, I would need another 4 or 5 hours, which I don't have in this course. So I just want to point out to you the fact that you need, for special track work, requires their own plinth design. I already showed you the direct fixation fastening systems for special track work. In transit systems, very often you don't have simple crossovers. You have usually multiple crossovers, double crossovers, all of which require their own special track work design. Traction power. You either uses for at grade, for above, for embedded track, you very often use catenary poles. For underground, you're using third rail. In all cases, the running rail acts as the negative return for the traction. Which takes me to embedded track. Okay, so let's talk a little bit about embedded track. Again, the big example in Israel with embedded track is Jerusalem. Jerusalem is primarily embedded track, with the exception of the bridge. So embedded track is track that is commonly used in light rail track running on the surface. In a lot of transit system designs, the embedded track is used only in the downtown or central business district, and then ballasted track is often used when you go out of the downtown area and you go into either the outside the downtown area or your embedded track area. So it's a question of system design. So in Jerusalem, for example, you're really embedded track almost the entire way. In many light rail systems around the world, however, you have embedded track downtown, ballasted track going outside of the downtown area where you can grade separate the ballasted track from the embedded track. Embedded track is considered to be a fairly difficult and expensive type of track to construct, and we'll talk about those. But one of the major issues in design with embedded track is maintaining the proper geometry and construction tolerances, as well as maintaining your electrical isolation, acoustic attenuation, and there are real issues associated with maintenance in embedded track. Embedded track is probably one of the most difficult tracks to do maintenance after construction. So again, you've seen this picture before. There's a embedded track with a very sharp curve, reverse curve. Again, down through a downtown configuration. So definition, embedded track is the track is completely covered except for the top of the rail. The only thing exposed in embedded track is my running rail, be it grooved rail, girder rail, or T-rail with some sort of flangeway design. So the flangeways can be formed, as I said, by using grooved rail, grooved rail, as we talked about here. Or it can be formed with some sort of flangeway material. For example, one design, which I'll show you in a few moments, uses T-rail with a bolted-in flangeway element. And theoretically, it's also possible to form a flangeway with the embedded material itself, but that's really not very, that has a major concern, because there the back of the wheel will quickly, and I mean very quickly, if you just relied on this material for the flangeway, an asphalt or a concrete or a brick paver structure, the back of the wheel, which is what runs against here, will very quickly start causing widening of this flangeway, wearing away of the much softer asphalt or paver or concrete layer. So usually it's desirable to have some sort of steel flangeway, either by a girder rail or by a external flangeway component.
Can I have a question?
Yes.
This bolt, this hole in the rail, doesn't make it less strength, and also can cause to break?
Yes, but it's the same problem we had with joints in the rail. Remember the problem with joints in the rail?
Yeah, it seems the same. So why to do something?
Because your vertical loads are much lower. An embedded track is usually used in light rail transit. So light rail transit will have a half to a third, so very often light rail transit, you're dealing with 8 to 10 ton axle loads. as opposed to 22 to 25 ton axle loads in UIC rail and 30 odd ton axle roads in heavy haul rail. So because your axle loads are much lower, your stresses in the holes are much smaller, and so so your potential for fatigue. Now, having said that, you still want to ultrasonic test your rail. You want to ultrasonically test your rail always. You always want to ultrasonically test your rail to look for defects in the rail, be it bolt hole, be it a cracks in the hole, or be it defects in the head of the rail, or being subsurface fatigue type of defects. So you're always going to be ultrasonically testing for this type of defect, but your risk of developing a bolt hole crack type defect is lower because your stresses are almost a third of your stresses for standard UIC rail, for standard UIC loading. But I'm a great believer in ultrasonic testing, so we always want to do ultrasonic testing. I know we haven't spent a lot of time in ultrasonic testing here. I'm going to see if we can at least get a little bit. As a matter of fact, I may just very quickly touch on ultrasonic testing after this, just because I think it's important enough to do that, and then we'll go to CWR. So I'm going to I'm just going to give you a piece of the ultrasonic testing just so you can be a little bit familiar with it. Okay. So again, the standards will vary depending on the design we're going to use, and this is not a course in standards. I'm not going to go through the detailed standards. I'm more interested in having you understand the engineering behind it. One of the issues that you run into with a light rail system is wheel width. Even when you're using grooved rail, if you have an excessively wide wheel, you run the risk of contacting your external pavement, whatever the pavement is. And whenever a steel wheel hits a pavement, it's not a good thing to do. So traditionally, a lot of LRT system uses wheels that have a narrower tread than a traditional passenger railway system, or even a metro on slab track. A metro on slab track, which is using a T-rail or a flat bottom rail, can have a conventional wheel tread width, because you don't worry about the outside of the wheel contacting anything. On an LRT, this becomes an issue. So design of your wheel width becomes really important. So you can have wheel widths as small as 50 millimeters, and also narrower flanges to keep it from coming outside. Some of the more modern LRT systems have a complete wheel width of the order of about 130 millimeters, or about 5¼ inches. Again, to reduce the overhead. The other thing that you do is you tend to raise the rail a little bit above the embankment, but the problem is how much can you raise the rail? So if you raise the rail by about 6 to 10 millimeters, you can avoid contact between the edge of the wheel and the embankment material for a while, until the rail wears down 6 to 10 millimeters. The problem with 6 to 10 millimeters of rail wear you will get in a couple of years. The other problem with projecting the rail too high is that bicyclists can run interference, or pedestrians can trip over this. So most of the time you're dealing with embedded track in a pavement where you have pedestrians, you have bicycles, you have rubber tired vehicles. I was involved in a lawsuit a couple of years ago where a bicycle tire got caught in the gap between the embedded rail and the pavement. And the tire and the bicycle rider got flipped on his head, got injured, and sued the Metro, and it was a very messy type of situation. So while you can project the rail, be it the groove rail or the T-rail, 6 to 10 millimeters above the track, you can't do much more than that. And 6 to 10 millimeters is certainly within the wear zone. Not, you're talking about years rather than talking about months, but you can still wear down. 6 millimeters of wear is not a excessively high amount of wear for running rail. And then you also have the issue of vertical deflection. Now, amount of vertical deflection you have is a function of the stiffness of the embedded track. But we see embedded track deflecting of the order of 1.5 to 4 millimeters. So if you're 6 to 10 millimeters above the top of the rail, even that new, you're gonna deflect down 1.5 to 4 millimeters. So you start getting 2 millimeters of wear, and you're at the higher end of the deflection range. You can start have interference between the outside of the wheel tread and the top of the flangeway. So again, there's a whole design trade-off. And so this is not an isolated design. You really need to design the width of the wheel, the size of your embedded rail, the amount of deflection you're going to have, and the elevation of the embedded rail above the pavements. All must be designed together to minimize the amount of contact you have between the tread of the wheel and the pavement. Because again, let's go back to the picture because it's easy to show the picture. Remember, my wheel is running over here. So I have, let me get a different color that at least shows a little bit better maybe. Oh. My wheel flange is running here. This is my flangeway right down there. My wheel is running here, and then I got to just be careful that the edge of my wheel doesn't contact this pavement over here. And I have to take into account the size of the rail, the width of the wheel, the height of this rail above the pavement, and the amount of vertical deflection I have under load. Because I will see at least 1.5 to 4 millimeters of vertical deflection. You also have to make sure you have sufficient flange height, because you don't want your flange to be too narrow and pop right out. Okay, we start talking about embedded track types. We got two major types of embedded track, non-resilient, and let me go back to yellow. Non-resilient and resilient. With non-resiliency, with non-resilient types of embedded track. Now, what's a non-resilient type of embedded track? The most common one is just make it all asphalt. I just pour asphalt under the rails, around the rails, through the side of the rails. That becomes a non-resilient embedded track. So how do I attenuate dynamic loads? Some LRT systems use resilient wheels. I don't think they're all that effective in protecting the track, but they're good for protecting the passengers. If I want to make sure I reduce the impact for my passengers, resilient wheels work, but the resilient wheels aren't all that effective in protecting the track. So we need to define the track structure's resiliency based on the load distribution and the type of embedded track that we're looking at. Okay, so like I said, non-resilient embedded track, it's on a hard base slab, concrete or asphalt with very limited ability to absorb the wheel impact, which means I need to rely on the vehicle system. Non-resilient track has had mixed success around the world. A lot of problems with spalling of the surrounding embedment and the surface failure. They're most successful really under very lightweight trams and streetcars. So like, for example, Philadelphia in the United States has rigid track for their streetcars because they're relatively lightweight. But they're a problem in high loading situations such as sharp curves. The most common technique used is the resilient embedded track. Jerusalem is an example of a resilient embedded track design where there's resiliency built into the support of the rail as well. So the theoretical goal, the design goal, is to duplicate rail deflections and resiliency inherent in ballasted track. You really don't achieve that, but that's the goal, to try to do that. So what are the types of resiliency elements that are used? One of the more, okay, so let's look at my different resilient elements. Okay, the first one is using a boot or a simple elastomeric pad underneath the rail. The elastomeric pad is just vertical. The boot gives you a little bit more elasticity around. It also gives you some advantages in protecting the base from moisture. Another element that introduces elasticity is in the support of the railhead, where you can use rubber or some sort of elastomeric cement bitumen or some sort of element that has some other elastomer that has resiliency in here. And then I mentioned pads. Some systems have hypothesized just putting buttons underneath the track. Not commonly used, but I've seen it in the literature. So here's an example of one type of resilient track structure design, which has incorporated drainage elements. You can see this particular one uses a regular flat bottom T-rail. This uses, there's a rail boot that goes around the base of the rail, provides resiliency, and also to try to prevent moisture from coming through. These elements here tend to be some sort of epoxy cement or something with a little bit of resiliency in it, so that you introduce some resiliency in here. This is an example of a rail design where there's a bolt going through the base of the rail holding these steel elements over here. So you can see it creates a flangeway over here. And then these are elastomeric elements. So we have steel We have a rubber boot on the base, and then we have elastomeric elements away from the flange. So again, remember the wheel is over here. This is designed to accommodate a slightly wider wheel because you have this large flangeway on the other side as well. And then you can build your pavement up out here, however way you want to do it, your street pavement. Again, bricks, fillers, design, concrete, blocks, asphalt, whatever you want in here.
Excuse me, Professor.
Yeah.
By resilience, do you mean holding the stresses?
No, by resilient, I mean
Control?
deflects under load. Like rubber is a resilient material. You press down and you have a soft spring, low stiffness,
Okay.
relatively low stiffness. Rubber or some sort of other, the term is elastomeric because it's elastic. It has a high degree of elasticity, high degree of springiness, if you want to think of it that way. You compress,
So
you can compress it and you can
control-
release.
So controlling the loads, not the stresses.
You're really not using it for full support. It's like in this particular system, most of the load is being distributed through the base of the rail as normally, but it's giving you some elasticity by this introduces some elasticity, some deflection under load for dynamic load attenuation. Yes.
Mhm.
This is another system. This happens to be a Vossloh system. It's called W-Tram, manufactured by Vossloh. Again, you can see this uses a grooved girder rail. Here's a spacer, elastomeric spacer, to provide some support and to provide some resiliency into the structure. There's also a pad underneath here. This is a full-size boot. This is a boot you can see that goes completely around the girder rail. Usually you would put some filler again in here, but this is designed to protect the girder rail from moisture and provide some resiliency throughout. And you can see it actually has a shape factor in the bottom here. You can see the shape factor. That's designed to provide improved resiliency, also designed to get rid of heat. Whenever you see a design like this, it's also designed to get rid of heat as well as provide additional resiliency. This is an interesting idea. This is an idea that they developed in Germany. The idea here is actually very clever. The idea is, why do I need a full girder rail? I mean, a standard girder rail is sitting on a base, and the argument is, why do I need all that? So let me just chop that off. And so I only had the head of my groove rail. That's in an elastomeric element over here, and that's into another filler material over here with another elastomeric pad over here, some sort of epoxy, some sort of plastic external coating, and then whatever I want to put in my street over here. So I'm basically making this channel, which is formed by this blue component out here. You can see my drainage elements through here, and you can see my grooved rail heads. This is called an LR55 embedded rail track. I know there are a couple of places in Germany that are using this. I'm not familiar with anybody else that's using this other than the Germans.
Well, the disadvantage of this is it sounds like it's better for noise and vibration. And
Yes.
it's better for a current.
Yeah, it has some advantages.
Yeah, but what are the disadvantages? It seems to be very interesting.
It is interesting. The disadvantage, one of the disadvantages is that it looks like it's a little bit on the expensive side. Because it's a
Okay.
fairly sophisticated system. You have 1, 2, 3, 4, 5 different layers of material, plus all the drainage components.
And maybe adjustment during construction.
There is no adjustment in this one. Adjusting this one will be a problem. This is one of those systems that if you get excessive wear, you have to go in there, dig it out, and replace it.
Yeah, so this is disadvantage.
Yes,
Okay.
but you're right. It's a very interesting system because it has, you know, it has some very fundamentally interesting structure to it. And then we have the Allan system. I think it does. Is Jerusalem using a variation of the Allan system?
Yeah, yes. Also in Tel Aviv.
I thought Jerusalem was using of it. So
Also Tel Aviv.
say again.
Tel Aviv also.
Tel Aviv also. Okay. So this is a very common one. This was, I think, developed in the Netherlands. If I remember correctly, this came out of the Netherlands and has gotten a lot of application and a lot of use out worldwide. So you can see this is using, you know, here we actually specify an RI60N rail, so that's a 60 kilogram per meter grooved rail over here. This is a cork, elastic cork material. My understanding, it's a very specialized type of material that's made out of cork and some sort of elastomeric binder that provides resiliency as well as being a filler in here. You can see how it goes completely from the top of the rail throughout here. This goes into a concrete or steel trough. So you have your street, very similar to what you saw with the German ones. You basically dig out this big square box. You put this concrete or steel trough in here. And then you fill the system in here. You have a pad on the bottom. I've seen versions where the pad is continuous in the longitudinal direction, and I've seen versions where it's discontinuous, like sleeper pads. You have a pad, you have a gap, you have a pad, you have a gap, you have a pad. I've seen both versions in use. So we have your rail with your pad underneath. And then you have your elastic cork material here. And then do whatever you want in the street in between. Again, everything requires stray curb protection. And let me stop here and see if anybody has any questions. I sort of went through this very quickly because there's a lot of detail. I have a version of this presentation that's about twice as long, but I don't literally have the time for this class to do this. As a fact, you know, when I only added this last year because there was so much interest in talking about this. So anybody have any questions about what we've covered, which is a lot? Okay. Let's stop sharing this. And I was going to do CWR first, but I realize I keep referring to to ultrasonic testing, and I'm not sure people understand what I'm talking about when we talk about ultrasonic testing. So we're going to go. I'm going to do a short version of this. This is in Moodle. So if you want to look on your own, you can, but I want to sort of get you a little bit familiar with this before I go back to CWR. Okay, so this was actually a very famous derailment in the United States because it was political. I don't know if you remember when Hillary Clinton was running for president. Well, before she was president, she was a senator from New York, and she was already planning to run for president. And so they had this big derailment in upstate New York, and she was a senator, and she made a real big political stink out of this derailment, caused all sorts of embarrassment to the railroad. I'm not going to go through the details of it, other than I want to show you what the broken rail looked like. This was the derailment that occurred. Look at the size of that defect at the time it broke. This was a very, very large defect. And one of the things that it shows is that you can't really you can't really know when it's going to when it's break. It can break anywhere from a small percentage of head to a large percentage of head. So one of the differences in practice in between the heavy axle load world and the UIC world is the UIC world will allow a small defect to remain in track until it gets large enough to be taken out, in their opinion. And Israel Railway Standards, for example, allows that. In the heavy axle load world, they don't. In the heavy axle load world, you find any defect, you take it out because you're afraid it's going to fracture under the next big dynamic load. That becomes an issue of standards and where you take your rail out. But the obvious question is, how do you find this kind of defect? This defect is, all this damage in the top of the rail had happened after the derailment, not before the derailment. All this thing grew underneath the rail, and you're seeing they're half fat, dumb, and stupid, just like the Hatfield derailment that I showed you in an earlier class. So how do we find defects? We use ultrasonic testing. What's the matter here? Why don't I have a wider? There we go. All right. So ultrasonic testing is the most commonly used technique in the world for finding internal defects. And every railroad in the world that I know uses it in one form or another. And not only railroads, but metros and light rail transit systems. Everybody uses ultrasonic testing because it works. It's pretty effective. It's about 90% effective, which is pretty good, even though not good enough, but it's, research is going on to keep making it better. Okay. So ultrasonic testing can take place from either rail-bound vehicles or high rail vehicles, which are highway vehicles with railroad wheels, or through hand push carts, which I'll show you in a few moments. The big issue with ultrasonic testing is the speed of testing. The speed of testing for ultrasonics is of the order of 25 to 40 kilometers per hour is the speed of testing, which means you can't run ultrasonic testing cars in between your trains. These nice ultrasonic testing cars, they can travel at 100 kilometers an hour or 150 kilometers per hour, but they have to test at between 25 and 40 kilometers per hour. So what's the theory of ultrasonic testing? It's very simple. I have an ultrasonic probe. I have an ultrasonic crystal. Sorry, I have a little crystal inside this probe. You see, this is actually a handheld probe, which I can push along the track. It issues a pulse, an ultrasonic pulse. If there's no defect, the pulse goes all the way to the base of the rail and bounces back. Since I know the frequency and I know the speed of this pulse, and I know the speed of this pulse with rail steel, and I know the height of the rail, I know the amount of time it's going to take me to go down and back. And by the way, that's why it's speed limited, because I have to have enough time to go down and back to bounce back. And so if by looking at the speed echo of this ultrasonic signal, I can see that this is a clean, or if I have a defect, like this bolt hole crack, you can see I'm not going to go all the way down to the base of the rail before I get deflection. I'm going to deflect much earlier. And so my time signature is going to come very earlier. So my scan signal of my ultrasonic is going to reflect as much earlier reflected time. And that's the whole principle of ultrasonic testing. Now, the two most common ways of using it in the field is to embed the crystal either in a rubber-filled wheel or to use a shoe like this, a sliding shoe. The rubber-filled wheel is much more common. This is the rubber-filled wheel. Here, you can see here there are different crystals. So by orienting crystals in different directions, I can look at different types of defects. So in this particular case, I have a 0-degree crystal, which is straight up and down. So this is a 0-degree crystal. I have a 70-degree crystal, which is actually going out of the plane of the paper. So it's actually going to the railhead, and it's designed to look at transverse defects, which is what the network rail did not do when they had the Hatfield derailment, which they had to do afterwards. And then I have a 45-degree crystal that's going after defects in this plane, like this type of bolt hole crack. And the wheel is rubber filled. Excuse me, the wheel is water filled. Water is a good conductor of ultrasonic signals. And in addition to that, there's a couplant, which is usually water used between the wheel and the top of the rail. So you can see here, there's a water spray. And that water spray is a couplant for your ultrasonic signals. I'm sure many of you have gone to the doctor and have had some sort of ultrasonic exam. If you're a woman and you had a child, you've certainly had ultrasonic pregnancy testing to look at the condition of the baby. Men who have prostate problems are always getting ultrasonic testing there to look at bladder filling. So and anybody who's had an ultrasonic testing, remember they put this big thick jelly on you and they put the probe on the jelly. That's the couplet. Well, we can't afford jelly going down thousands of kilometers of track. So we use water, or water with some sort of antifreeze if it's going in the winter, so to make sure the water doesn't freeze. So a water antifreeze mixture is the most common couplet used in the railroad world. Here you can see a sliding shoe configuration. Here's actually a sliding shoe in visibility. Here you can see the sliding shoe, but you can see the different angles here explained. So here you can see my 0-degree angle going up and down. Here's my 70-degree angle going not only to longitudinally, but transversely. So this is coming out of the plane as well. I have a 30-degree angle coming out of the plane here. I have a 70 out here. I have a 35 coming down and back. So here you can see the crystals. Here's my 0-degree crystal. Here's a 35-degree crystal. Here's a 70-degree crystal. You can see my different crystals clearly oriented here. Now, why do I need the different crystals? Now we can go through an easy explanation here. A 0-degree crystal shoots my ultrasonic probe down here. So it has no problem finding defect number 1, completely misses defect number 2, and if defect number 3 is very small, it's going to miss defect number 3 as well. To find defect number 3, I need a probe that comes out this way. To find defect number 2, I need a probe that goes down in that angle. And to find a defect down here, I need a probe that goes down here. So there's my 70 and 35 degrees. Also, my 35 degrees is used for the bolt hole cracks as well. These are the signals that will come out. This is called the A scan. This is called the B scan. Here you can clearly see your time signal. Here, this is a variation of the time signal. This B scan is actually the more commonly used scan in the railway industry. Here's an example of a B scan showing These are normal bolt holes. So these are just bolt holes due to a joint bar. And this is a defect underneath underneath the head of my rail. This is a head and web defect that's coming right underneath there in the gap between the joint bar. Interior of an ultrasonic car. Right now, ultrasonic cars are still manually manned, where we use computer and AI, artificial intelligence, to supplement the operator. We're not yet at the point where artificial intelligence has completely taken over the operator. We talked about defects of being 3 different planes. Remember, we talked about the transverse plane, the horizontal plane, and the vertical plane. So again, you have to make sure you have ultrasonic detection to handle the different planes that you're dealing with. We talked briefly about this, I believe, already: small, medium, and large size defects. For example, Israel Rail Standards allows you to keep small defects in place. And once they get to a critical size, you have to take action. Some of the European standards are the same way. Currently, US standards, for example, is any defect you found, you have to take some action. The action is a little different based on the size. The action is more dramatic for a large defect than a small defect, but you have to take some action even for a small defect. We talked about reliability of the ultrasonic testing. One of the issues with reliability is a function of defect size. So when you get to a very large defect, you have an extremely high reliability, 95 to 99%. When you have a small defect, the reliability goes down. So typical reliability for this magenta graph over here shows you some fairly common reliability curves that shows you that for a defect, it's about less than 5% head area. So a defect with this defect is less than 5% head area. The probability of finding it is less than 50%. For a defect less than 10% head area, the probability is about 80%. For a defect that's about 30% head area, it's about 90%, and about 50% head area is about 95%. So you can see that there's a fairly high probability of missing your smaller defect. Now, that often is the determination of how frequently you have to test, because it takes tests and this research has shown that to go from about a 5% defect to about an 80% defect or a 90% defect can happen for certain classes of defects in the order of 20 to 30 MGT, which in a very busy line could be 6 months. So it means you better go. So if you find a small defect, it can grow very quickly, which is again one of the reasons why, at least in heavy axle load worlds, they take out small defects. In the lighter axle UIC world, where it takes a little bit longer for the defect grow, they allow smaller defects to remain in place. I'm not going to spend a lot of time on this because I want to get to CWR. Just very quickly, the measurement of a defect. If you have a defect at an angle, a 0 degree probe will find this defect, but it'll underestimate the size of this defect. It'll say this defect is 10 millimeters, when in fact this defect is 32 millimeters in length. A 35 degree curve will give you a much more accurate measure of the defect. This is just defect reliability. If you have a surface shell or a surface rolling contact fatigue, that will hide the defect, because the ultrasonic signal will bounce off of that surface defect and say, hey, I have a surface defect, which you can also see, but you can't tell there's an ultrasonic defect underneath it. That's one of the problems associated with defects that form detail fractures from shells underneath rolling contact fatigue. The shell can disguise the detection of the defect. Magnetic induction has also been used. but it's not as commonly used. It's often used as a supplement, not even often anymore. It's sometimes used as a supplement, but it's not as commonly used as ultrasonic. Everybody uses ultrasonic. Okay, the last issue I want to talk about real quickly is scheduling inspections. And what's happening is we're moving the world, the railroad world is moving to what we call risk-based inspections, where we monitor the number of, we adjust the number of inspections as the rail gets older and our defects get more common. So remember our friend, the Weibull rate equation. This is the first derivative of the Weibull equation. So this is defects per mile per year or defects kilometer per year. Okay, so remember, as the rail accumulates more MGT, the number of defects per kilometer per year or per mile per year increases. So what happens is that if I have a 100 miles, which is what, 150, 160 kilometers of railroad, and I look at my defects with time, and let's say I inspect every 50 MGT. Let's say my standard is to inspect every 50 MGT. And this is a 50 MGT railroad, so I'm inspecting once a year. Okay, so the first time I inspect, I don't get a lot of defects. The second time I inspect, it's a little bit more. By the time I get out here, I'm looking at 150 defects over 100 miles. Since my ultrasonic inspection is only about 90 to 95% reliable, I have a high risk of missing the defect and getting a derailment. So what I want to do, and what I'm evolving to do, is as my number of defects get more frequent, my testing interval is going to be less. So I start off every 50 MGT. Well, here, for example, I don't even test till I get to about 200 MGT. Then I go 50 MGT. Then I go 25 MGT. Then I go 12 MGT. Then I go 12 MGT here, 12 MGT here. I adjust my inspection interval based on the number of defects I get, or my defect rate. So a very simple way of doing this is to fix the number of inspections so I have one defect per mile per inspection. So if my defect rate is one defect per mile per year, I test once a year. If my defect rate is 2 defects per mile per year, I test two times a year. If my defect rate is 3 defects per mile per year, I test 3 times a year. If my defect rate is 6 defects per mile per year, I test 6 times a year. This is a technique that a lot of railroads have adopted. There's another technique, which I am not going to go into because of the interest of time, which is a service defect-based detection system, because we know from test data, let me see. Service defects are defects that are missed by ultrasonic. So if I'm at a 90% rate, and if I find 5 defects per mile per year, which is a lot, I need to replace the rail, the odds are I probably had another 0.5 defects per mile per year that were not detected by ultrasonic. Those are the surface defects. And those are the ones that are related to my highest risk of derailment. So if I adjust my inspection rate based on the service defects, I can significantly reduce my derailment rate by a factor of 2 or more. This is, by the way, is actual data from a railroad that's adopted this. So this technique, and you're welcome to read on this of your own. And if you're really interested, I can give you some literature references on this. This is something called risk-based adjustment. And it's the same principle. It's designed to decrease the inspection interval, increase the number of inspections per year as the number of defects increase. And I look at both my detected defects and my non-detected defects. I cover a lot of material here in a short period of time. Let me throw this out for questions. Anybody have any questions? I really wanted you to understand the basics of ultrasonic inspection, because I don't care what railway you are. If you're Israel Railways, Jerusalem Light Rail, Tel Aviv, I don't care where you are, you're going to be doing ultrasonic inspection.
Alan,
Yes.
here by decreasing the intervals, how do you decrease the defects? By taking care of the defects earlier?
You're
How do you reduce
first
the
of all, you're
defects?
finding defects earlier.
Yeah.
So the odds are you'll find a defect when it's a 20% head area and not let it run to the risk of a 40% head area, which is good because it's less likely to break under a 20% than it is under a 40%. You're not necessarily reducing the number of defects, you're just finding them earlier and you're finding them more reliably so that none of them get past your inspection and break under your train.
You can take care of them at
Yes,
time.
you can exactly. That's exactly the purpose. So you can take care of them in time so that they don't result in a broken rail, because the risk of a broken rail and a derailment is very high. You say your signals are going to pick up the broken rail. That's fine, but what happens if the rail breaks under your locomotive, which happens? And so if the rail breaks under the locomotive, it doesn't make a difference if your signal's red. You're just broken your rail underneath your locomotive.
Yeah.
And if the locomotive happens to make it over, the wagon behind the locomotive will derail.
Okay.
So yes, you're giving yourself more capability to find the defects early and effectively.
So for inspection, we have categories, or we have some kind of regulations.
In one of the presentations I gave you earlier, and I didn't have time to spend on it, I actually went through Israel Rail's category of defects. I think I spoke about it very briefly.
Yes.
But yes, defects are always categories based on size. Let's go back. Defects are always categorized based on size. Sometimes it's percentage of head area. Sometimes it's just physical size. Like Israel Railway standards for this type of defect, for a detail rail for fracture, is based on the length of the defect, how big the defect is over here. So if the defect is 5 millimeters, there's one action. If the defect is 10 millimeters, 20 millimeters, 30 millimeters, is another action. And some of the other defects, like the longitudinal defects that I showed you in an earlier class, those are always categorized based on ties, and action is always tied into the size of the defect. And ultrasonic tech inspection will tell you the size of the defect. So it'll tell you how big the defect is, as well as the presence of the defect. Okay.
I have two questions.
Okay.
Those actions that you just said about, let's say, small defect size, did you mean what you teach us before about lubricating and grinding? Are those
right, yes.
actions?
Well, lubrication doesn't really help you with defects. Grinding does. If you recall, and I went through
To prevent bigger defects.
It actually prevents defects from forming. We have fewer let me put it this way, it delays the formation of the defects. So instead of a defect starting to come at, say, 400 or 500 million gross tons, the defects may start coming out at 700 or 800 million gross tons.
So once you detect a defect, it doesn't really matter. It doesn't help to grind.
Once you defect the defect, remember, defect is local. You're replacing 10, 12 meters of rail. When you're
Okay.
the defect actually may only be 15 millimeters in width. The size of this defect may only be 15 millimeters in this width, but you'll usually replace about 12 meters of rail. But then if you start seeing defects, then you want to go out and grind the rail before new defects start developing. So once you have a defect, it's too late to grind it. Once you have this type of defect, you have to replace it. But you may have 40 kilometers of rail with the same amount of tonnage. So you can go out and grind that 40 kilometers of rail, yes, and that can extend the life of the rail.
Okay, thanks. Another question: does joints affect the ultrasound test?
The joints show up in the ultrasonic signature, but the joint has a separate signature. Let me see if I can go. Oh. There's actually a joint. There's actually a joint here, but we know it's a joint, and the operator and the AI can say it's a joint. And this is the bolt hole. And it doesn't show any bolt hole cracks, but if there was a bolt hole crack, we start seeing the cracks up here. And this is a head and web separation defect. So these are different types. These are different types of defects. These are the indicators for the bolt hole, for the joint and the bolt hole. So yes, you see the joints, but you can but it has its own.
But you can say it's a joint and not a. Okay. You can say it's a joint and not a defect.
So it's a different signature than a defect.
Okay, thanks.
Okay, let's take a short break, 10 minutes, and then I want to get into CWR. I want to try to cover CWR a little bit.